Welcome to WikiPodcast.
Yeah.
Imagine a universe where for every particle of matter, like the electrons in your phone or the protons in your body, there's an identical but opposite twin, an antiparticle.
Uh-huh.
And if these twins ever meet, poof, they vanish in a spectacular flash of energy.
Right.
This isn't just a wild thought experiment. It's the reality of antimatter. And lurking alongside it, influencing the cosmos in profound, almost ghostly ways, are neutrinos, the other hidden twin of the universe.
That's a great way to put it, yeah.
Today, we're diving deep into these elusive, fundamental particles, antimatter and neutrinos. Okay, so let's unpack this a bit. The idea of negative matter or, opposite matter, it's actually intrigued thinkers for centuries. But our modern understanding of antimatter, that really solidified less than 100 years ago.
What's truly fascinating here, I think, is how theoretical predictions often pave the way for these monumental discoveries. While Baudirac, back in 1928, he foresaw the existence of what he called anti-electrons just from his equations.
Just from the math.
Just from the math. And then just 4 years later, Carl Anderson actually confirmed their existence experimentally, naming them positrons. It wasn't just, a footnote. It was this profound moment. It revealed that sometimes the universe kind of whispers its deepest secrets to us first through mathematics.
And challenges us to find the proof.
Exactly. Challenging us to then go out and find the experimental proof.
So it's clearly more than just like a scientific curiosity. These fundamental twins, they play a crucial role in everything from, medical imaging to the very fabric of the universe itself.
Absolutely. And this immediately raises a really profound question that physicists are still grappling with. If matter and antimatter are so fundamentally similar, why does our observable universe seem to be almost entirely composed of ordinary matter?
Right. Where's all the antimatter?
Exactly. There's hardly any antimatter around compared to matter. That imbalance is one of the biggest cosmic mysteries out there.
That's the universe-sized question. But okay, before we get deeper into that cosmic puzzle, let's just define our terms a little better. At its core, antimatter is simply material composed of antiparticles.
Uh-huh.
Think of them as mirror image partners of ordinary particles. They have the exact same mass, but their electric charge is reversed.
Right, so an electron is negative.
Its antiparticle, the positron, is positive. And beyond charge, they have other mirrored quantum properties, like something called parity, which basically means their spatial orientation is flipped.
And even particles without charge, like neutrons.
They have counterparts, too.
Yep, antineutrons. And their internal components, the quarks inside them, they have their charges flipped compared to a regular neutron's quarks. And this is where the interaction gets truly dramatic. When any particle meets its antiparticle partner, they don't just gently neutralize, they undergo mutual annihilation. Poof is right. It's a spectacular burst of energy, where their entire mass gets converted into intense photons, usually high-energy gamma rays, and sometimes neutrinos or other less massive particle-antiparticle pairs.
Wow.
And this isn't just theoretical, it's a perfect, undeniable demonstration of Einstein's famous equation, E-mc². That tiny bit of mass transforms into an astonishing amount of energy.
It's astounding the power contained in such small particles. And these antiparticles, they aren't just isolated oddities. They can actually bind together, just like ordinary particles do, to form antimatter.
Right, like atoms, but anti-atoms.
Exactly. For instance, a positron and an antiproton can form an antihydrogen atom. And scientists have, even with incredible difficulty, artificially produced nuclei of antihelium.
Which are the most complex antinuclei we've managed to observe so far.
It just goes to show, right? If matter can exist, so too can antimatter, at least in principle.
And to really stretch our minds for a moment, there are some interpretations in quantum physics, like the intriguing Feynman-Stoeckelberg interpretation. It suggests that antiparticles behave identically to regular particles, but are, in a sense, traveling backward in time.
Whoa, backward in time. Seriously.
Well, it sounds like science fiction, but this concept is actually used in modern particle physics diagrams. It's a useful mathematical tool. But to bring it back to something more tangible, rest assured that antimatter behaves gravitationally just like regular matter.
Ah, so it falls down, not up.
It falls down, not up. Yeah, this was recently confirmed by experiments at CERN involving antihydrogen atoms, and that's a really foundational piece of the puzzle for understanding how antimatter fits into the universe.
Okay, so that's antimatter. Now let's talk about the other hidden twin in our deep dive, neutrinos. When we say ghostly, we really mean it.
They really are.
Neutrinos are almost massless, fundamental particles that have no electric charge. They interact incredibly weakly with ordinary matter.
So weakly, it's hard to even detect them.
Exactly. So weakly that trillions of them pass through your body every single second, mostly from the sun, without ever interacting with a single atom inside you. Just whoosh.
And what's truly remarkable about neutrinos, and why they're also sort of a hidden twin, is their ability to change flavors as they travel.
Flavors. Like ice cream.
Huh, not quite. They come in 3 types, electron, muon, and tau neutrinos, and they can oscillate or transform from one type to another as they fly through space.
Okay.
And this phenomenon, this oscillation, it proves they must have a tiny but non-zero mass. That discovery completely reshaped our understanding of particle physics.
Because the original theories said they should be massless.
Right, exactly. And because they're so abundant and interact so weakly, they carry unique information about the universe's most extreme events, things like supernovas or the very early moments of the Big Bang. They're like a window into processes we just can't see with light.
Ghostly messengers. Okay, now back to our cosmic puzzle.
Yeah.
Here's where it gets really interesting. The universe's great imbalance.
The big one.
Despite matter and antimatter being such perfect mirror images, the observable universe is almost entirely composed of ordinary matter. Not an equal mixture, which you might expect if they were created in equal amounts at the Big Bang.
Right, you'd expect symmetry.
But we don't see it. This profound asymmetry is one of the greatest unsolved problems in physics. It's what keeps cosmologists up at night.
This tiny, absolutely crucial excess of matter over antimatter is a central mystery. The hypothetical process where this slight inequality between matter particles, which we call baryons, the building blocks like protons and neutrons and antibaryons, emerged in the very early universe is called baryogenesis.
Baryogenesis. Okay.
But while the observable universe might be predominantly matter, it's crucial to remember that high-energy particle collisions happening throughout the cosmos do continually create minute quantities of antiparticles.
So antimatter hasn't completely vanished.
No, it's just incredibly rare and fleeting outside of specific, very high-energy conditions.
That's a crucial point. We actually see natural production of antiparticles happening all the time, right here near Earth. Positrons, for example. They're produced in certain types of radioactive decay, like beta-plus decay of naturally occurring isotopes. Potassium-40 is one. They also pop up from interactions of high-energy gamma rays with matter. And in neutrinos, another kind of antiparticle, they're created by the more common beta-minus decay. And get this, high-energy cosmic rays hitting Earth's atmosphere also produce antiparticles.
And even thunderstorms.
Thunderstorms. Seriously.
Yeah, observations have shown thunderstorms can produce positrons. Terrestrial gamma ray flashes, they call them. So it's not some totally alien concept. It's happening right above our heads constantly. And if we connect this to the bigger picture, observations by the European Space Agency's Integral satellite have shown this fascinating asymmetrical cloud of antimatter specifically, annihilating positrons around the galactic center.
In the middle of the Milky Way.
Yep. And this pattern actually matches the distribution of things called X-ray binaries. These are binary star systems, where one star is a black hole or a neutron star pulling matter off its companion.
Okay, very energetic places.
Extremely energetic. And this suggests these systems are a significant source of electron-positron pairs. We can detect their presence because when those positrons annihilate with electrons, they produce gamma rays with a very specific energy, 511 keV.
Ah, like a fingerprint.
Exactly. It's a unique energy signature, a cosmic fingerprint telling us exactly what happened there, electron-positron annihilation.
And it gets even wilder. Theoretically, whole antimatter galaxies could exist way out there in faraway regions, maybe left over from cosmic conflation in the early universe.
It's a possibility.
If they do exist, though, they would look observationally identical to normal galaxies, wouldn't they? Making them incredibly difficult to spot.
Pretty much impossible with standard telescopes. You'd need to look for something else.
Right, so NASA's actually trying to find evidence by looking for those unique X-ray and gamma ray annihilation signatures, maybe where superclusters of galaxies are colliding, hoping to catch, a matter galaxy hitting an antimatter galaxy.
Talk about cosmic fireworks. That would be an unambiguous signal.
Absolutely.
And adding to this picture, findings from the Pamela satellite detected antiprotons trapped in the Van Allen radiation belts around Earth. What's crucial here is that these antiprotons seem to originate from high-energy cosmic processes interacting with our atmosphere, not directly from the Big Bang.
So they're being made locally, in a sense.
Or at least trapped locally after being made elsewhere. More recently, data from the Alpha Magnetic Spectrometer, the AMS-02 instrument on the International Space Station, has shown some really intriguing patterns. Cosmic ray positrons seem to peak around 275 at GeV, which is interesting. It might potentially hint at dark matter annihilation as a source.
Dark matter creating antimatter. Wow.
It's one possibility people are looking at. And the antiprotons AMS-02 also have, on average, higher energy than the cosmic ray protons, suggesting they might be produced differently.
Not just standard collisions.
Maybe not. And the ongoing search for larger antinuclei like antihelium is yielding some fascinating, though still tentative, results. AMS-02 has recorded a few signals that are consistent with antihelium-3.
Antihelium, like 2 antiprotons and an antineutron.
Potentially, if confirmed, that would be huge. It could imply the existence of significant amounts of antimatter, maybe even anti-stars somewhere out there.
Yeah.
Still very early days on that, though.
Okay, given all this talk of cosmic creation and detection, it's natural to wonder, how do we even get our hands on this stuff here on Earth?
Yeah.
Artificial production efforts are, well, mind-bogglingly complex.
Extremely difficult, yes.
For positrons, scientists have generated large numbers by driving incredibly powerful lasers through gold targets. And there was a truly groundbreaking experiment in 2023 at CERN.
Ah, yes, the beam plasma experiment.
They created a record-breaking yield of electron-positron pairs, something like 1.5 times 10 to the 13 pairs, over a quadrillion, by smashing a massive 440 GeV proton beam into a target.
An astonishing amount of energy focused just right to create these pairs.
But producing complex anti-atoms, like antihydrogen, that's an even greater feat, isn't it?
That's so absolutely. After the initial hot antihydrogen production back in the 90s at CERN and Fermilab, collaborations like Athena and ETRAP managed to make cold antihydrogen around 2002.
Cold meaning slow enough to trap.
Exactly, slow enough to study properly. The process is incredibly intricate. You have to take antiprotons, slow them way down, mix them with an electron plasma to cool them further, and then carefully combine them with positrons in a series of complex magnetic traps.
Sounds delicate.
Very. And while they've made hundreds of millions of antihydrogen atoms this way over the years, the process remains astonishingly inefficient. We're talking less than 0.1% of the starting antiprotons actually forming catchable antihydrogen.
Wow. And once you finally made it, how on earth do you keep it? That's the next monumental challenge, right? Because antimatter cannot touch ordinary matter for even a fraction of a second without
Annihilating. Vanishing in that puff of energy. So for charged antiparticles like antiprotons or positrons, they use devices called penning traps. These use a precise combination of electric and magnetic fields to hold the particles suspended in a vacuum.
Okay, magnets and electricity. But what about neutral stuff, like antihydrogen? No charge to grab onto.
That's even harder. For neutral antimatter like antihydrogen, they use specialized atomic traps that rely on the particles' tiny magnetic moments. Basically, they have like tiny little compass needles. You use carefully shaped magnetic fields to hold them.
Still sounds tricky. What's the record for holding onto it?
The record for trapping neutral antimatter is held by the LFH collaboration at CERN. Back in 2011, they managed to hold hundreds of antihydrogen atoms for up to 1,000 seconds.
1,000 seconds, so about 17 minutes.
Around 17 minutes, yeah. Which sounds short, but in the world of antimatter containment, it was a huge breakthrough. And antiprotons, being charged and easier to handle, they've been held for an incredible 405 days in a penning trap.
Over a year.
Yep, but still, tiny quantities.
Which brings us to another point.
Yeah.
The immense cost and difficulty. It's widely considered the costliest material on Earth, isn't it?
By far. Estimates range from billions to even trillions of dollars per gram, if you could even make a gram.
Trillions per gram.
Yeah, the energy required, the infrastructure, the inefficiency, it all adds up. Even with advanced facilities like CERN's antiproton decelerator, producing just a nanogram, a billionth of a gram, could take thousands of years of continuous operation.
Okay, so mass production isn't happening anytime soon.
Definitely not. And this actually raises an important question for future research. Whether it might eventually be more feasible to try and mine naturally occurring antimatter, like those antiprotons trapped in Earth's Van Allen belts, or maybe even more concentrated belts around Jupiter.
Mining antimatter from space.
It's a long shot, but maybe, just maybe, it could potentially lower the cost significantly compared to making every single antiparticle from scratch using accelerators. Something to think about.
So why go to all this trouble and expense for something so ridiculously hard to make and keep? Well, antimatter actually has some astonishing applications, some already quite practical.
That's right. The most widespread is in medicine. Positron emission tomography, or PE scans.
These scans, right, I've heard of those.
In these scams, doctors use radioactive isotopes that decay by emitting positrons. These positrons quickly find an electron in the patient's body, annihilate, and produce those characteristic gamma rays.
The 511 keV ones.
Exactly, which detectors outside the body can pinpoint. This allows doctors to visualize metabolic processes, map brain activity, detect cancers, things like that.
So antimatter is already helping save lives.
In a very real way, yes. And antiprotons are also being explored for their potential in treating certain cancers, similar to existing proton therapy, but potentially offering even more precise targeting of tumors. Still experimental, but promising.
Okay, medicine is huge. What about the more science fiction applications?
Ah, you mean fuel for spaceships?
Exactly. Antimatter-powered rockets. Star Trek stuff.
Well, the theoretical potential is definitely there, and it truly captures the imagination. The energy density of antimatter is astronomically higher than any chemical or even nuclear fuel we know.
How much higher?
Consider this. Just 1 kilogram of antimatter reacting with 1 kilogram of matter could produce the rough equivalent energy release of 43 megatons of TNT.
43 megatons from just 2 kilos. That's mind-boggling.
It really is. A tiny amount could power incredible journeys. However, and it's a big however, there are significant challenges preventing us from building Star Trek-style warp drives anytime soon.
Okay, what's the catch? Besides making this stuff?
The main catch is the form the energy takes. The annihilation products are largely these high-energy gamma rays, which are incredibly difficult to capture and direct for thrust. They tend to just radiate away in all directions.
You can't easily point them out of the back like rocket exhaust.
Yeah, not easily at all. Plus, a good portion of the energy gets converted into unstable charged particles like pions and muons. These fly off, but they quickly decay, often into those elusive neutrinos we talked about.
Which just zip away, carrying energy with them.
Exactly, meaning not all the energy released by emissary is easily usable for propulsion. You lose a lot.
Right, so an antimatter-powered rocket isn't exactly around the corner then, is it? Seems like the engineering challenges are almost as big as the production ones.
They really are. Beyond the energy conversion issues, it's simply the amount needed. Even if we could efficiently harness the energy, producing the kilograms, let alone tons, of antimatter required for any significant interplanetary or interstellar mission is currently far, far beyond our capabilities. We're struggling to make nanograms.
Yeah, grams versus kilograms is a big leap.
And on a more sobering note, antimatter has also been historically considered theoretically as a potential trigger mechanism for nuclear weapons.
Oh, right, the ultimate bomb.
But again, the immense difficulty and the absolutely astronomical cost of producing antimatter in anything close to sufficient quantities makes this currently unfeasible for such purposes. It remains firmly in the realm of, well, speculation.
Good to know. It's a powerful reminder, though, of the raw energy contained within this exotic substance, but also of the monumental hurdles to actually harnessing it. So we've journeyed from the theoretical prediction of anti-electrons all the way to the practical trapping of actual anti-atoms. We've delved into the cosmic mystery of why we live in a matter-dominated universe.
The great
And even touched upon those ghostly, shape-shifting neutrinos and their profound implications for understanding the cosmos, from supernovae to the Big Bang.
It's clear, I think, that antimatter neutrinos, these hidden twins, they're not just exotic curiosities tucked away in particle physics labs. They are truly fundamental to understanding the universe's past, its present composition, and perhaps even its ultimate fate. They connect the very smallest scales to the very largest cosmic structures.
Which raises an important question for you, our listener. Given the incredible scientific potential, but also the immense cost and difficulty associated with understanding, producing, and maybe one day harnessing antimatter and neutrinos, how do you think humanity should prioritize its research and development?
Yeah, where should the focus be?
Should we primarily focus on solving those fundamental cosmic mysteries, like the matter-antimatter asymmetry? Or should the push be more towards developing practical applications like advanced medical treatments, or maybe, just maybe, pursuing that tantalizing possibility of interstellar travel someday? It's a profound choice, really, balancing that pure curiosity with more immediate potential benefits. Thanks for listening. Write us your opinion on this in the comments. Subscribe to the channel to help more listeners reach our deep dives. Thank you and have an amazing day.